If you want to use k and n, there's two things that you need to determine. One is your setting for the parameter k, and the other is a notion of what nearest means. We will discuss both in this video. In order to determine which k works best for our training data, we again split the training set into a training set and a validation set. We train the algorithm and then use a validation set to determine the best k. Note that for k nearest neighbor, there isn't really an explicit training phase like in other algorithms, except maybe building a data structure that helps us determine the nearest neighbor for a new point a little quicker than iterating through all of the points. Nevertheless, we again cannot use the test set for determining any settings of our algorithm, so we need the split into training and validation set. An even better method to evaluate different k on the validation set is the use of cross-validation. Now in cross-validation, we split our training set into k equally large subsets, and then use k-1 of these subsets as our training data, and the remaining one as the validation data. There are k possibilities to choose which one of the subsets we use as a validation set, and that leads to k so-called folds for the cross-validation. So here we do threefold cross-validation. Now we try out different settings for our hyperparameters and get the validation performance for each of those folds. We then choose the setting for the hyperparameter that on average performs the best on all of the folds. Finally, we use the whole training set to evaluate the overall performance of our model on the test data. For k and n, we need to be a little careful here because both our hyperparameter is called k and the number of folds is called k as well, but these are obviously unrelated. In the extreme case, we use as many folds as we have samples, and this is then called leave one out cross-validation, because for each of the folds, we omit exactly one sample of the training data. This is especially useful if we have not a lot of data and want to use as much as possible for training, but still get a good estimate of our performance. Unfortunately, this also means that we have to train our model n times, and this is not computationally feasible in all cases. So if our lack of data is not too extreme, and training our model is computationally very extensive, then it's better to just use one validation set or a lower number for k. Let's look at what the best value for k is in our example. Here we used 3 folds. And you can see the accuracy on each of the folds, as well as the mean for all of the folds in this plot right here. The maximum is assumed at k equals 7. So this is the setting that we will choose for k and n here. The second setting that we need to consider in k nearest neighbor concerns the distance measure, and therefore defines what nearest means. There are many distance metrics that we could use, and here are a couple of them. The Euclidean distance, or L2 norm, is the square root of the sum over the square root differences in each dimension. The L1 norm is just the sum of all the differences, and this is also called the Manhattan distance. The L infinity norm takes the maximum over all the differences. It also has a special name, and that is the Chebyshev distance. Then we can also measure the angle between two feature vectors, or we could compute the so-called Mahalanobis distance. And while its equation looks a bit involved, Essentially, this is just a linear transformation of our feature points, and then the computation of Euclidean distance in that transformed space. And we will see why in a minute. But first, let's visually look at these different distance metrics. Let's say we have two feature vectors, u and v. Then the Euclidean distance measures the length of the distance vector right here. The L1 norm computes the sum of these two lengths over here. By the way, it is called the Manhattan or city block distance because if we have a street map that looks like this, then the L1 norm is exactly what we need to compute for walking or driving distances. The max norm would just be the length right here because it's longer than the one over here. And finally, the angle can be seen right here. This list is of course not exhaustive. There are many more distance measures that we could use. One issue that is related to the choice of distance metric in K and N is that K and N is very sensitive to the scale of our data. So if we look at our data example again, and instead of measuring both features on the same scale, we measure one of it in meters instead, then for k equals 1, the decision boundaries look a lot different. Fortunately, there's a very easy way around that, and that is data standardization, where we use the mean and variance of our data to scale each feature so that it has 0 mean and unit variance. This is something that is done very often in machine learning because there are many algorithms that are sensitive to differences in scale. Another possibility is to use the Mahalanobis distance. And if this matrix right here, sigma, is equal to a diagonal matrix that has the variances in each feature on the diagonal, that would be equal to normalized Euclidean distance. And if sigma is equal to the covariance matrix of our data, then that would be the exact same thing as doing data standardization. Another thing that can cause some problems for K and N, or in general in machine learning, is the curse of dimensionality. Let's say we have discrete data between 1 and 10. Then if we randomly draw 20 samples, it could happen that our data covers exactly 100% of the input space. If we add a second dimension to that, with the values for the second dimension again varying between 1 and 10, and randomly draw 20 samples, in this example, the data covers just 18%. Adding the third dimension only makes matters worse. Now we are only covering 2% of the input space. For K and N, that means that the nearest neighbor will be pretty far away. It also means that in order to cover our whole input space, the number of data points n has to grow exponentially with the number of features.